Imagine an interstellar traveler, a mysterious object that journeyed for millions of years through the cold, dark reaches of deep space, suddenly bursting into a spectacular flare as it reached perihelion, the closest point in its orbit to the Sun. This was 3IATLAS, an interstellar object unlike any other previously observed, whose sudden explosion caught the attention of astronomers, astrophysicists, and space enthusiasts worldwide and raised urgent questions about the nature of interstellar comets, the physics of solar proximity, and the hidden secrets these cosmic visitors carry. The explosion was unexpected and unprecedented, defying conventional understanding because no interstellar body observed so far has exhibited such a violent, concentrated release of energy without a clear external trigger or catastrophic collision event. Its behavior challenged assumptions about how objects formed in other star systems react when exposed to intense solar radiation and tidal forces, demonstrating that the universe often operates beyond our simplest expectations from the earliest observations. 3.1. exhibited properties that hinted at its potential for extraordinary activity. Its elongated shape, irregular rotation, and subtle wobbling indicated a complex internal structure possibly containing layers of ice, metallic compounds, and volatile gases, unlike regular comets, which tend to exhibit gradual sublimation and steady outgassing as they approach the Sun. 3.1. behaved in ways that suggested hidden internal stresses and highly reactive materials. The object's velocity and trajectory, carefully tracked by NASA, JAXA, Harvard, and ESA observatories, provided a precise path, yet no one could predict the explosive reaction at perihelion, demonstrating that even detailed orbital calculations cannot fully anticipate the internal behavior of interstellar visitors. 1. Leading hypothesis involves extreme solar heating, triggering rapid sublimation of volatile materials trapped within. The comet's interior, unlike conventional solar system comets, 3IATLAS, may contain compounds that react violently to high temperatures or possess complex layering that traps volatile gases in high-pressure pockets. The sudden exposure to intense solar radiation could have caused these pockets to rupture violently, releasing dust, gas, and possibly plasma. In a sudden and dramatic eruption, the thermal stresses generated by the Sun's heat may have fractured sections of the comet, weakening structural integrity and precipitating the explosive release observed. From Earth-based and space telescopes, this suggests that interstellar comets may possess unpredictable internal structures that respond non-linearly to environmental changes. Unlike comets formed in the relatively stable conditions of our solar system, the comet's rotational dynamics further amplified the stress. During perihelion, the elongated shape and irregular spin created uneven centrifugal forces, placing additional tension on regions already weakened by solar heating or sublimation of volatile materials as 3IATLAS approached the Sun. These combined stresses may have reached a tipping point, triggering fragmentation or explosive outgassing patterns that produced a sudden increase in brightness and the ejection of numerous fragments into space. The irregular rotation and wobble also complicated predictions of where and how fragments would be expelled, creating an intricate and asymmetric debris pattern that astronomers were eager to study. Spectroscopic analysis revealed a highly unusual chemical composition that likely contributed to the explosive behavior the comet contains. A mixture of metals, silicates, and ESOs, in ratios rarely observed in known solar system comets. Some compounds may be exotic or previously unknown, originating from its home star system where different chemical processes dominate. This unusual chemistry could explain why certain regions reacted violently to solar heating while others remained relatively stable. The ejected material, containing dust, ice, and volatile compounds, provides a rare window into interstellar chemistry, allowing scientists to study materials formed under extreme conditions, billions of kilometers away from Earth. High-energy interactions with the Sun may have also played a crucial role. The comet's proximity to intense solar X-rays, ultraviolet radiation, and magnetic fields could have triggered additional energy release mechanisms within metallic or magnetically responsive compounds in its interior or surface layers. These interactions may have contributed to plasma formation, ionization, or localized heating, amplifying the explosive outgassing observed from telescopes across the globe. By studying multi-wavelength data, including visible light, infrared, ultraviolet, and X-ray observations, scientists are piecing together a detailed picture of how the Sun's energy can trigger such extreme behavior in interstellar objects. Global scientific collaboration was critical in capturing the sudden event. Observatories from the United States, Japan, Europe, and Australia coordinated to observe 3IATLAS before, during, and after perihelion, the fragments. Dust ejection and brightness increase were meticulously analyzed to estimate the energy released, the likely internal structure prior to explosion, and the potential for surviving fragments to continue their interstellar journey. Comparisons with other interstellar objects like Oumuamua provide context, highlighting that 3IATLAS's violent perihelion reaction may be unique or rare, offering invaluable insights into the diversity and behavior of objects traveling between star systems. The explosion also raises profound questions about the life cycles of interstellar comets. How do these objects survive millions of years in the harsh environment of deep space, only to react unpredictably when exposed to a powerful star? Could explosions be a natural mechanism for redistributing interstellar material, seeding planetary systems with dust, ice, and complex compounds? Scientists continue to explore these possibilities, recognizing that each event like this is both a scientific treasure and a challenge to existing theories about cometary, physics, and interstellar object evolution. Public fascination has grown. Alongside scientific investigation, the sudden explosion produced a dramatic visual spectacle, captured by telescopes and relayed to audiences worldwide through media, social platforms, and science blogs. The brightness, fragmentation, and mysterious cause of the event ignited curiosity, discussion, and debate, reminding humanity of the dynamic and often unpredictable nature of the cosmos. These public reactions also highlight the importance of science communication, showing that extraordinary cosmic events can inspire wonder, while providing an opportunity to educate audiences about astrophysics, chemistry, and orbital dynamics. NASA, JAXA, Harvard, and ESA emphasized caution in public statements, focusing on verified data and minimizing speculation while analyzing the explosion in detail. The gaps in immediate public reporting often give the impression of secrecy, yet they reflect the time needed for meticulous analysis and verification before drawing conclusions. The complexity of the event, combined with the novelty of studying an interstellar object under extreme solar influence, necessitates careful peer review and cross-observatory validation. Before sharing results with the wider public, the fragments ejected during the explosion are themselves of enormous scientific interest. Each fragment carries information about the comet's interior, composition, and structure prior to the event. Studying their trajectories, rotational behavior, density, and composition allows researchers to reconstruct the internal stresses and reactions that led to the explosion. These observations are helping scientists refine models of how interstellar objects respond to extreme environmental conditions, enhancing understanding of not just 3IATLAS, but the broader population of interstellar bodies that may visit our solar system. Comparisons with other interstellar visitors provide additional insights. Oumuamua, for instance, did not exhibit explosive behavior, highlighting that interstellar objects can vary greatly in composition, structure, and response to stellar radiation. This diversity emphasizes the importance of observing each visitor in detail, recognizing that generalizations about interstellar comets may be misleading and that unique events, like 3IATLAS's perihelion explosion, are invaluable for expanding knowledge. The sudden perihelion explosion also has implications for planetary defense and space exploration. As interstellar objects pass through the solar system with unpredictable behaviors, understanding their structural integrity, fragment behavior, and potential for sudden energy release is crucial for risk assessment, mission planning, and spacecraft shielding designs. The event serves as a natural laboratory for studying high-energy processes in space and provides lessons for safely navigating or intercepting objects that may one day approach Earth. The sudden explosion of 3IATLAS at Perihelion reveals the remarkable complexity of interstellar objects and their interactions with stars. Even after millions of years in deep space, the object contained hidden energies and reactive materials that only revealed themselves under extreme solar influence. Its elongated shape, irregular rotation, unusual chemical composition, fragment patterns, and interactions with solar radiation collectively produced a rare cosmic phenomenon that challenges assumptions, inspires scientific inquiry, and captivates public imagination. The event underscores the vastness of what we do not yet understand about interstellar matter and reminds us that each cosmic visitor is an opportunity to learn, discover, and marvel at the intricacies of our universe.